Good morning to all. I am Dr. Thayalan from Radiologic Physics Foundation. Today we are going to present a new lecture, Particle Interaction with Matter. This is the part 4 of the Interaction of Radiation with Matter lecture series. First of all, we see what is a particle. Particle is one which has mass and occupies space. The particle may have charge or do not have charge. The particle includes proton, electron, neutron, positron, alpha particle, beta particle, and heavy nuclei. In general, we can call them heavy charged particle, light charged particle, and chargeless particle. What are the heavy charged particles? Proton, alpha particle, heavy nuclei belongs to this category. Light charged particle is nothing but electron. Chargeless particle is neutron. So we can have the interactions as heavy particle interaction or light particle interaction or neutron interaction like that. Now what is actually very important is the electron is a very light particle and it is 1 by 2000 times lesser mass compared to proton. Behavior of heavy charged particle is totally different from lighter particles. Particles have some common features. What are the features of the particles? Particles do have path length and range, and they does ionization and excitation. They perform BREMSSTRAHLUNG process. They gives radiative loss of energy, collisional loss of energy, and also they appear with the Bragg peak. What is actually this path length and path range? Suppose if you take an electron as shown in the figure A, electron will travel like this. It undergo a lot of scattering to this. So if you range, the range is only from this point to this point. The path length is actual distance traveled by the particle. So the path length of the electron is higher than the range. Suppose if you take a heavy charged particle, the path length is equal to the range. So this is because the heavy charged particles goes in straight direction without undergoing any scattering. Let us see what is ionization. Ionization is nothing but removal of orbital electron from a neutral atom. How it happens? When a particle comes to the orbital electron, the electrical forces interact with the orbital electrons. Suppose if they have like charges, they get attracted. If they have unlike charges, they get repelled. So it is nothing but Coulomb force of interactions. It can be either attractive forces or repulsive forces. In ionization, part of the energy is used to overcome the binding energy of the orbital electron. The remaining energy goes as kinetic energy of the ejected electron. As a result, an electron and a positive atom is formed. This we call it ion pairs. What is the energy required to produce such ion pair? The energy required to produce such ion pair in air is 34 electron volt, whereas in the case of soft tissue, it is 22 electron volt. What happened after the ionization? Ionization is followed by characteristic X-rays and Auger electrons, which has been explained in the previous lectures. The ejected electron is capable of causing secondary ionization, and such electron is called delta rays. What are the conditions for ionization? The condition for ionization is that the particle energy should exceed the binding energy of the orbital electrons. The delta ray may have sufficient energy to cause further ionization in the medium. For example, a 10 kilo electron volt electron may produce about 450 secondary electrons of energy 10 to 7 electron volt. Majority of the charged particle interaction involves outer orbital electrons. Let us see what is excitation. Excitation refers moving of an electron to a higher orbit by supplying energy. The particle transfers its energy to the orbital electrons. The transferred energy should be less than the binding energy of the electron. Transferred energy will be spent in molecular vibrations as infrared emission, visible and ultraviolet radiation, etc. Excitation energy loss is lesser than that of ionization energy losses. Let us see what is the Bremsstrahlung process. The particle may overcome the electron cloud and goes nearer to the nucleus of an atom. Interaction takes place between the particle and the nuclear field. Suppose if the particle is a heavy charged particle, the interaction leads to production of positron emitters. For example, carbon 11, sodium 13 and oxygen 15 in tissue. Suppose if the particle is light charged particle, nucleus can exert strong electrical force on the particle and the particle may be deflected. Light charged particle like electron undergoes this type of process and get deflected. The deflected particle undergo deceleration and loses energy gradually, which is called Bremsstrahlung X-rays. So what is Bremsstrahlung? Bremsstrahlung is due to interaction of electron particle with the nuclear field. Let us see what is radiative losses. Particle energy loss per Bremsstrahlung process is called radiative losses. The probability of radiative losses is equal to q square z square divided by m square e square. Q is the charge of the particle, Z is the atomic number and m is the mass of the particle, E is the energy of the particle. Bremsstrahlung production depends on how the particle is closer to the nuclei. If the electron is very closer to the nuclei, stronger will be the Bremsstrahlung X-rays. In contrast, if the electron is away from the nucleus, lesser will be the Bremsstrahlung X-rays. It is likely for light charged particle like electron and is negligible for heavy charged particles. It is likely to happen in high atomic number medium. What is collisional losses? The particle energy loss due to ionization and excitation are called collisional loss. It can be an inelastic collision. Some part of kinetic energy is converted into another form of energy or absorbed in the medium. The rate of energy loss is proportional to the electron density of the medium. Collisional loss depends upon the atomic number of the medium and the kinetic energy of the particle. In general, it can be written as Z divided by kinetic energy of the particle. Z is the atomic number. It is also useful to discuss the ratio between the Bremsstrahlung energy loss and the ionization energy loss. It is equal to kinetic energy of the particle and atomic number divided by 82,000. It's a mere number. So it gives you actually the ratio of the Bremsstrahlung energy loss versus ionization energy loss. For example, in the case of 10 kilo electron volt to 10 MeV energy, ionization energy loss dominate over the excitation. So coming to the heavy charged particles. The heavy charged particles have stopping power, specific ionization and linear energy transfer. Let us see one by one. What is stopping power? Stopping power is the average kinetic energy loss per unit path length. What is the unit? It is million electron volt per centimeter. If you divide the stopping power by density, it is called mass stopping power. What is the unit? Million electron volt centimeter square per gram. What is specific ionization? It is the number of primary and secondary ion pairs produced per unit path length of the charged particle. So it is given by specific ionization equal to q square by v square. Q is the charge of the particle, v is the velocity of the particle. In addition, we can also define what is linear energy transfer, that is LET. It is the amount of energy deposited per unit path length in a medium. The LED is proportional to Q square by Ek. That is, Q is the charge of the particle, Ek is the kinetic energy of the particle. Alpha and protons are high LED radiations. They deposit energy at shorter range, causing much damage to the cells. Alpha particle soft tissue is 1.4 micrometer compared to 200 micrometer for electrons. That means the alpha particles are deposits in a shorter distance compared to the electrons. LED is also referred as restricted stopping power. That means it is defined above certain energy. It is not covering the all energies of the emitted in the medium. Specific ionization. What is the difference between specific ionization and LED? Specific ionization accounts energy losses before the ion pairs are produced, whereas LED is a measure of average energy deposited in the medium per unit path length. Let us discuss what is Bragg peak. In the medium, depth increases, the particle deposits energy slowly and it becomes slower and deposits more energy at a particular point and it appears as a peak. This is called Bragg peak. So Bragg peak particle loses energy, slows down and spend longer time in the location, resulting higher rate of energy loss as shown in the peak. This is called Bragg peak. The upper peak is for alpha particle, lower peak is for proton. Alpha particle Bragg peak is bigger than the proton Bragg peak. What happened beyond this peak? Beyond the Bragg peak, the particle reaches thermal energy, picks up electron and become electrically neutral in the medium here. So that means there is no exit dose for this particle when it is actually used in the patient. Bragg peak property of the particle is used to treat cancer patient in proton radiation therapy. Single proton beam width is not sufficient to cover the tumor volume, hence multiple beams are used. Proton delivers maximum radiation at a given depth without exit dose. It is an established precision radiotherapy. Light charged particle like electron do not have Bragg peak. Coming to the light charged particle can go inelastic and elastic collision with orbital electron and atomic nuclei. Let us see what is inelastic collision with the atomic electron. Inelastic collision with atomic electron gives rise to ionization and excitation, leading to collisional losses as discussed before. The electron interaction with atomic nuclei gives rise to BREMSSTRAHLUNG process, leading to radiative losses. Elastic collision between electron and electron leads to electron scattering. There is no energy loss. Similarly, electron-neutron elastic scattering may take place. This is called multiple Coulomb scattering or nuclear scattering. So coming to this neutron interaction, as we told, neutron is having no charge. It do not have charge. No such Coulomb force of interaction takes place here. But it performs direct collisions. There are three types of collisions reported. One is elastic collision with the nuclei, inelastic collision with the nuclei, and neutron capture. Let us see one by one. The first, inelastic collision. Energy is distributed between neutron and nuclei. It is called neutron moderator. So moderators are used in nuclear reactor. Fast moving neutron prefer this type of elastic collisions. In inelastic collision, the neutron is absorbed by the nucleus, which goes to an excited state. The excited state nucleus releases neutron and gamma rays. This is possible in high energy neutrons with heavy nuclei. This is what is called neutron resonance scattering. On the other hand, in neutron capture, neutron is absorbed by the nuclei and gamma rays are emitted. The very good example is cobalt-60, which is the source used in telecobalt missions. Slow moving thermal electrons prefer this type of interactions. Neutron easily penetrate in the medium because it has low cross section. Its energy loss depends upon the direction of the neutron and the nuclei after collision. Energy transfer is poor in high Z material. Neutron proton collision gives maximum energy transfer happens. Hence, hydrogen rich material is used as neutron shield. What are heterogeneous material? Paraffin wax, polyethylene and plastic. So that is the reason why heterogeneous materials are used as neutron shields wherever it is needed. What happened to the lead? Lead is a good shield for X-rays but poor towards neutron shielding. I hope you enjoyed the video. We will come back with another video in the next session. Kindly subscribe and succeed. Thank you very much.